Okay, so now let's have a bit of recap of what we discussed in the last lecture. So I think we already know about camera geometry. So camera geometry is basically about how to project a point in the 3D to a point on the image. So this is basically the camera geometry concept that we need to transform a point in 3D, which is 4 by 1 and 3 by 4 into 3 by 1. And P here equals to what? Anyone remember? What is P? What is P? No one knows? It is consists of intrinsic and extrinsic parameters. By the way, you have to know this. When I say you have to know, means that it will be in the exam. K, R, P. Okay, so that is the extrinsic K and intrinsic K and extrinsic are P. Right. So this is one thing that we learned, and this one, to get these parameters of KRT is what is called camera calibration. So this one is belongs to camera calibration process. Right. That's one thing. The second thing, we learn about fundamental metrics. And what is fundamental metrics? Anyone knows? What does it mean by fundamental metrics? What is the definition of fundamental metrics? If we have x prime t multiplied by f, which is the fundamental matrix, and the other point x equals to 0. And x prime here, x and x prime are corresponding points. Corresponding points in different images, of course. So if you have two images, one point here and the other point there are exactly the same point, representing the same point in the world. I mean. So there is a corresponding points between x and x prime. And why these x and x primes are important? What is the point that this? Why do we need to have these points? Why this is important? Anyone? Question here. Why important? The answer is actually on the slide here. So what is the point then? Why this is important? Because this is about stereo. Stereo need to have a corresponding points. Imagine that if you close your eyes, one of your eyes, close one of them, can you see the depth? Well, you can still see the depth, but that one is memorized depth. It's not really the depth that you just come to your eyes, but you remember that this is the depth that you see with your two eyes. If from the beginning, I mean, when you are born, unfortunately, perhaps you only have one eye, you don't have any sense of depth, because you don't really have the capability to know depth. And to know depth, you need to have the corresponding point, right? If you don't have the corresponding point, for example, you will not know the depth. So that's why this x and x primes is important. And one of the property of x and x prime is that when you multiply them with fundamental matrix, it gives you 0. And it's very strong constraint here. Right? So mathematically, that's why this, first of all, this is the starting point. That's why you have to know why that one is important. The second point is that there is a constraint. The constraint for these points for these pairs of points is that they are connected by a fundamental matrix. Now, in this case, as I mentioned again, you have to imagine there's a point there in the world, and you see this point from two angles. You see this point from two angles here. And this is the line of sight. And this is your camera one, C. And this one is the point of C prime. Then X bar is here, or Xi bar, and Xi bar prime is that point. So it is governed by this geometry, which is called triangulation. So this triangle here is called triangulation. Okay, so the geometry of this is called epipolar geometry. So the geometry that governs all this is called epipolar geometry. And in this epipolar geometry, we also have a line connecting E prime. E prime here is called epipole. And there is a line between epipole and your point. And this green line here is called L prime. And L prime here is called, anyone remember what is the name of L prime? It is called, yeah, epipolar line. So now the question is, well, I can make a statement that this epipolar line is very important for stereo. Now the question is why? Why this is important? Question here. Why important? Anyone can answer this? Why this epipolar line is important? Anyone? Well, not in human perception perhaps, but in for computers to find the depth from stereo, this epipolar line is very important. The question is why? So now imagine that if you are doing a computer based computation of the depth, then what you have to start with a point, a pixel. And this one is your starting point. Well, you can use the right image or the left image, it doesn't really matter. But let's start with the left image. From the left image, you are given a pixel. So, and it happens that the pixel is this one. This is the pixel that you are working on, target pixel. Right? And you want to know what is the depth of these target pixels. You want to know what is the depth of that particular pixels. Then what do you need to do if you want to compute the depth of these pixels? What do you need to do? Is to find the corresponding point at the other side. So that one is important. The green part is important. You have to find the corresponding points in the other image. And now the question is that given X, how can we know X prime? Where search, exactly, with search, right? Then how do we can do the searching? Exactly, along the epipolar line. Of course, you can search for the whole image, but that will be very, very expensive. So you want to reduce the space of the search. And this one gives you a good constraint on how you need to search on the other image. Any questions here? And that's the reasons why this epipolar line is important for stereo, because it can constrain your search to find X prime in the other image. Any question, anyone? So now the question is, of course, mathematically, we know that it's important now. So mathematically, how can we compute L prime? So what is L prime here, right? And L prime, this is the reason why fundamental metric is fundamental, is important, is because when you multiply f, assume that you know f, multiply it by x prime, then you will get L prime. So that's how important it is to have fundamental metrics. Because using fundamental metrics, given the pixels, then suddenly you can have the line on the other side that crosses the target pixels. In this case, x prime. Any questions, anyone? So this and these two, number 2 and number 3 are important. All right. Okay. So that's the last thing that we discussed about this fundamental metrics. And the third thing before the research week was rectified image. So what is rectified image? Rectified image is when your image, your stereo, has a digital arrangement in a way that you have x here, so you have xi, and then you have xi prime. So your x will be different. So x1 and x2 or x prime here, x and x prime, x and x prime, they are, sorry, without the bar, x is not the same as x prime. They are different. But for the y-axis, they are the same. So y equals to y prime. This is called rectified image. Rectified image is in the situation where your corresponding points are at the same horizontal line, at the same y-axis, but different in x-axis. So if you look at these two diagrams, right? So when I say two, is that these two diagrams, this one and this one. Both of them are in the yellow box here. So what is the connection between these two boxes? What is the connection between these two diagrams? Anyone can spot the connection between these two diagrams? These two diagrams have some or similar property, right? What is the property that is similar between these two diagrams? They have this information of the line. In the first one, in this one, the number 1 here, using fundamental metrics, you will get the L prime. So L prime will connect xi and x prime. And in number 2 here, which is rectified image, you also have this red line. This red line here is actually the same as the red line in the first one. So in other words, we can use fundamental metrics to rectify any images. You can convert the first one into the second one using fundamental metrics. If you know your fundamental metrics, you can convert the triangulation, the epipolar geometry setting into rectified images. And why do we want to have rectified images? Why don't we just want to stick with fundamental metrics scheme or diagram there? Well, there is no difference between these two. Number 3 is only for your easy understanding. Actually, there is no difference between these two, but for us, it is easier to work on 3 because we just use the horizontal line to get the corresponding points. Right? And we will start with these rectified images for your assignment. But again, they are the same thing. If you know fundamental matrix, it doesn't really matter whether this is rectified or not rectified. Because you can just use the equation here. You can use the equation, this equation, to find the line. Well, not really that easy, but it's doable. I mean, not as easy as rectified image, but it's still not that easy. Okay, so that's the idea of these rectified images. So we can have a line, horizontal line, to do the searching. Any questions so far here for the recap? So by the way, for this rectified image, how we can get the depth, right? So that's the question, how can we get the depth? The depth in this rectified image is very simple. You can just have D. D is called disparity. And this disparity is actually a function that is proportional to the inverse of the depth. So G here is the depth. G is the depth. So disparity is actually inverse of depth. Okay, so it's not exactly the 1 over Z, but it's a proportional. It's a constant here. You can assume that it's constant here, which is proportional to the inverse of the disparity. So when people talk about disparity, it's basically about depth because they are closely connected to each other. And now the question is, how we can know the depth? I use my phone. Use my phone here. Yeah, but I will take it. Okay, sure. Thank you. All right. So this is disparity, and the disparity can be computed by having the absolute value between x, the distance between x and x prime. So it's very simple. You can just look at the distance between x and x prime, and that's your disparity. Again, this disparity only works in this definition of disparity here only works for rectified images. If your images are not rectified, you cannot use this equation. Any questions so far? So to give you the more concrete illustration, I already prepared here rectified image, a pair of rectified images. So on the left, you have a target pixel. So this is your target, right? The target pixels that you want to know the depth. You want to know what is the depth of this target pixel. And because it's rectified, you can just look at the horizontal line here that is the same height of these target pixels. So the blue line is the line that indicating the epipolar line. In this line, there is a corresponding point of this red pixel. And the corresponding points here, or corresponding pixels here, as you can see, is in the corner of the car. And in the corner of the car will associate with this one, right? So the correct one will be this point there. So there's the correct point. There's the corresponding point that we want to find. But of course, we do not know. Computer doesn't know that one, the blue point, is the corresponding point. And then we have to search. How can we search the corresponding points? How can we get the blue point? Anyone? How can we get the blue point? What is the matching cost or the objective here? Anyone? What is the objective? If you have to create an objective function, what kind of objective function that we have to have here? How can we do the matching? No, we don't use it because this is for all pixels, not just selected pixels. Well, we can use sieve for just for the description. So sieve has 4, right? 4 steps. We just abandon the 3 steps and just use the last one, which is the descriptors. We can use that. It's a valid argument to have that, but it's too costly. What will be the simplest one? Again, the matching here has to be done for every pixels. It's not just key points. The difference between what and what? Well, how do you do the matching of pixels? If you are given a pixels here, how can you find the pixel on the other side? It's not projection matrix because we don't have the projection here. We do not know the corresponding there. If we know this one, if this know that corresponding that one, it will be, the problem will be finished already. We don't need to do anything. But the problem is that this one is difficult to find. Now we have to find it. We have to search from the left to the right. How can we search? How can we know that this is matched to the pixel that we want to find the target, to find the depth, the target pixels? Anyone? The simplest one. Don't think too much. I think you know the answer, but you think too much, and then you has doubt in your mind. RGB. Yeah, RGB. It's as simple as that. So this one is RGB value, right? This is RGB value. I1, G1, B1. Every pixel here, every pixel along the way have RGB value as well. R2, G2, B2, for example. Then what you do? How can you compute the distance between these two? How can you compute the distance? If they are exactly the same, then it is possibly that's the point of the corresponding point, right? If it is the distance is 0, so if the distance between this one is equal to 0, then this is highly possible or probable that the 2 point pixels are corresponding to each other. If they are not 0, if they are a large number, for example, definitely they are not corresponding points, right? So that's what we want, to find the RGB distance. In this case, RGB distance means the L2 norm, for example, or L1 norm, it doesn't really matter, right? When I say L2 norm, L1 norm, anyone confused with these terms? If you're confused with this term, please raise your hands. Okay, so I assume that you know that. So basically, this Euclidean distance is L2 norm. So we get the distance between every pixels there and find the lowest. And that's why this one is the lowest now, if you are lucky, right? But most of the time, you will not get this kind of graph. Why? If this target pixels happens to be part of the car, and what is the color of the car? White. And it's likely that assume white is 200, 200, 200, right? So if it is along this blue line, how many pixels that have white pixels? Well, many of them. We do not know for sure, but many of them, right? In other words, if you just use RGB, pixel-based RGB, then the proper, distance function will be like this. Because there's a lot of white pixels in the region, in the car regions. Then what is the problem? The problem is there's a lot of ambiguity, a lot of possible solutions along this line. So if there are a lot of possible solutions using 1 pixels, what do we do? If you are the programmer to solve this problem, what do you do? Exactly, increase the size of these pixels. So instead of just 1 single pixels, we use a square here, right? And this square can be 2 by 2, 3 by 3, 4 by 4, or even 10 by 10, or whatever the things that you want, depending on the resolution of your image. So if we use this, there will be less ambiguity because the surrounding will be different, right? So the surrounding here, for example, if this corner here, combination of the white surface and the road, the pedestrian road there, then it gives you some profile, for certain profile. Right? But if it is too small, if the size of the patch or the window is too small, what happened then? Well, there will be still a lot of ambiguity. Not as extreme as if you use 1 pixel, but still there are many ambiguities. Then what happens if you increase the size, become larger and larger? What happened then? If the size of your patches or your windows are too big, too large, what happened then? It will give you, in terms of the matching, it will be nice. The matching will be very unique, and you have one solution. But the problem is that your depth will be too rough. So if your pixel patch size is 5, you have very, very noisy depth. And if you have 85, which is too large, it will be not too sharp. The depth will not be too sharp. And if it is in between, maybe if that will be nice, right? But now, in this case, we use patch uniformly across images. Regardless whether they're unique or not unique on the surrounding, I mean, we always use the same size of patch. So you treat the patch size uniformly across the image, which is not really necessary. So there are 2 problems here in our discussion. First, we do not know whether this is too small or whether this is too large. To find the numbers is difficult. There is a trade-off in these numbers. And secondly, even if we get nice number, for example, 35 is a nice number, we have to apply this 35 size of pixels of patch across the whole image uniformly. We don't really differentiate between pixels. And that's not nice. The question is why? Why having the same size of patches for the whole image is not nice? Well, the answer is the same as this one. Why? Because if the patch is very, very textural and unique, for example, this patch here, I assume that a certain patch, for example, the tree here, right? The tree here, I think it's very unique. Even if you choose a small patch, it's very unique. The tree will not be repeated, the structure of the trees, of the leaves, will not be repeated that much. So even if you just have a small patch, it will be able to find the corresponding in the other image. If the patches are very textured. But if the patches are not very textured, for example, this road here, the road here, right? The road here, there are a lot of road here that is quite the same in terms of the color. This one is a bit textureless. So for the textureless surface, you want to have big patches. So then you can find unique profile in the other image. All right. So there's the problem here that in this strategy to use patch, although this solve the problem to some extent, it doesn't solve 100%. It doesn't give you good algorithm to deal with this problem. So again, our goal here is to find parameters the size of the patch size that can give us optimal depth estimation. That is sharp but not noisy. And that's the problem statement that we want to solve. And this is important. So you have to understand this. If you don't understand, please ask. Any questions, anyone? Okay, good. So I assume that you understand the problem. And from this on, we will try to solve this problem. We want to find a way, an algorithm that is better than this one. That's better than manually setting the size of the patch. And the solution for this problem, for our course, there are many different solutions, by the way. But in this course, I choose a method called Markov random field. So this one is called Markov random field. How many of you know about Markov random field or heard about Markov random field? Anyone know about Markov random field? How many of you know about Markov chain? Okay, Markov chain is great. So at least you know something there. So this one is Markov chain is one dimension, normally used in natural language processing or a sequence of events. But Markov random field is field. Field here means 2D or 3D or certain dimension. And of course, in this case, we apply for 2D. Okay, so let's learn a bit about Markov random field. So Markov random field, MRF, is part of a field, a greater field called graphical model. Graphical models. Okay, so now the question is, what is graphical models, right? Well, the concept of graphical model will start with an image. The concept of an image. An image is what? If someone asks you, what is an image? Well, there will be a lot of different definition of an image, of course. But in terms of mathematics, an image can be defined as a set of numbers representing light intensity or light brightness, and they are arranged orderly, so they are not random, they are arranged orderly in a 2D space. So we can define in this way, we can define an image in this way. So because they are arranged orderly and not random, means there are some connection. This means that there are some connection between pixels. So this means that we have connection or correlation between pixels. Correlation between pixels. And that's the motivation. We want to know what kind of correlation that we can have here, right? So basically, we want to find the correlation, to find the spatial correlation. And to find this spatial correlation, one of the way is through graphical model. And what is graphical models? A graphical model is a probabilistic model, probabilistic models that consists of consisting a graph express or expressing the conditional dependence between random variables. So there are a few keywords here that are very important. That's why I write carefully here. So the first thing that we have to keep in mind is that this is a graph. Okay, so basically we will learn about graph. And in this graph, there are conditional dependence between random variables. Okay, so you have to understand these three different terms here. Graph that can express the conditional dependence between random variables. So as you can see here, we have to look at the probability theory to understand graphical model. So some of you, I think many of you have taken or have been taking pattern recognition. So I don't really want to go into the basic probability theory here, because I assume that you know some basic about probability. So, but anyway, so I just want to have a very, very quick recap on the probability theory. Probability. So the things that you need to really understand about probability in this context, in our context, is that there are two rules in probability. Two rules. What are those two rules? Anyone? Some rule, yes, some rule here. The other one is product rule. That's right. So there are two rules here. So product rule, assuming that you have two type of variables. So here you have independent variable and you have dependent variable. For independent variables, if I have x and y, right? X and y, and there are independent variables, then P of x given y equals to what? Equals to P of x, right? That's called independent variables. And the product rule for this independent variable is that Px joint property of x and y equals to what? P of x multiplied P of y. And if they are dependent, the product rule will be what? P of x given joint property of x and y equals to P of x given y multiplied by P of y. Yeah, that's this independent dependent variable for product rule for dependent variable. And for some rule is always dependent variables. Again, if I have dependent variables x and y, P of x equals to what? Anyone? P of x equals to integral of P of x joint property at y dy. So this is called sum rule. Or this in discrete is a sum over y pxy. Okay, so this is sum rule, and you have to be fluent in product rule and sum rule, because otherwise you will get confused. along the way. And this is the most basic one. The second most basic knowledge that you have to know is Bayes' theorem. In Bayes' theorem, if I have x and y, for example, Bayes' theorem is that Px given y, which is called what? What's the name of this? Yeah, this one is posterior, equals to P of y given x, Px divided by P of y. So the first one is called likelihood, and the second one is called prior. Okay, so the third one here is called evidence. Right. So in this case, I will not explain all the details, but the things that are important from this Bayes rule is MAP. MAP is a maximum a posteriori. MAP means what? MAP means that we want to maximize, if you want to know about x, for example, x is the random variable that we do not know, and we want to know the value of x, equals to R max over x, all the possible value of x, P of x given y. So that's called maximum a posteriori. And in this maximum a posteriori, we can say that arc max over x is Py given x, Px. And again, this one is a likelihood, and the second one is prior. Any questions here, anyone? If you don't understand, please ask, because I assume you understand this, because we have discussed this a lot in pattern recognition course. But if those who are not taking pattern recognition, you might have difficulty to understand this. So please ask if you don't understand. Anyone has questions? No questions? Okay, so let's move on. Right. So now, in the definition of graphical models that we wrote here, right? Graphical model is a probability model consisting of a graph expressing the conditional dependence between random variables. So we need to know the meaning of conditional dependence here. The meaning of conditional dependence is very simple. It's basically, let me think. So we have conditional dependence, and of course we have conditional independence. So it is easier to explain from the second term here, conditional independence. Conditional independence, as we discussed a moment ago, is that if x1 given x2, x3, x4, for example, if you have 4 variables, and it happens that x2 and x4, so x1 is independent from x2 and x4, for example, then this one equals to P of x1 given x3. So this is called conditional independence. It means that x1 only depends on x3. So that's why it means that if it is conditional dependence, then x1 actually depends on x3. Okay. So it's a bit abstract here, but don't worry too much. I will explain further down. So then there is a correlation between this one and stereo and the depth from stereo problem. Another important things about Markov random fields is called factorization. So what is factorization? I can illustrate in this way. Imagine that this is pixels, but instead of two-dimensional pixels, I just choose a sequential pixels. So imagine you have 4 pixels, right? And if you want to, let's put a name here. So x1, x2, x3, x4. We have 4 pixels. And we want to have a joint probability. We want to know P of x1, x2, x3, x4. Right? We want to know the probability of this. So it means that if all are independent, so assume that x1, x2, x3, x4 are independent to each other, dependent to each other, dependent on each other. It means that you have to connect this one because x1 dependent on x2, x1 also connect to x3 because x1 and x3 are dependent to each other, and then x3 and x1 and x4, and then we have to have this x2 and x4, x2, x3, x2, x4, and x3 also connect to x4. Oh, sorry. I put the wrong connection. So if they are all dependent to each other, again, let me put in this way. Then they have to connect each other. Basically, they have to connect each other one by one. Because this is sequence, let me think. So this one connect with this one. Let me think. It's better not to have sequence, but immediately in the field. So let's put in the field. So we have x1, x2, x3, x4. It means that x1 connect to x2, x2 connect to x4, x1 connect to x3, x3 connect to x4, x1 connect to x4, and that one. So this one is, it means that all of them are connected to each other. So in this case, the meaning of this expression, the meaning of this probability expression is quite complex. Why? Because we want to know, assume that the value of x2 and xr here, the value is a just binary value. For example, 0 or 1. So each of these x1, x2, x3, x4 is either 0 or 1. Okay? So assume the value only of 2 options, 1 or 0. So in this case, this expression of P of x1, x2, x3, x4 means that we want to know what happens if it is x1 equal to 0, x2 equal to 0, x3 equals to 0, x4 equal to 0. So we want to know the probability of this. That's the meaning of that. Or we also want to know what is the x1 equal to 0, x2 equal to 0, x3 equal to 0, x4 equals to 1. We also want to know what is the probability of x1 equal to 0, x2 equal to 0, x3 equals to 1, x4 equal to 0, and so on and so forth. So if you have to do this, to compute this expression here is very, very expensive. How expensive are they if you have 4 variables? 2, 2, 4. Right? That's only when you have 4 variables. Imagine that your image is 1000 by 1000 at least. then you can imagine how many computation that you have to do in order to find this expression here, the probability of all pixels connected to each other. That's how we express an image in the probability model, that we have to connect all pixels, the corner in the pixels here and the corner pixel there have to be connected, and all pixels have to be connected to each other because they have a correlation to each other. And for these reasons, if you have to connect this in this way, it will be very, very expensive. So we don't want to do in this way because we know that it's not possible to model in this way. But this one is the ideal one. Very, very ideal when we connect all pixels together. And all pixels are dependent to each other, right? So this is one extreme. So here, number one is one extreme. The other extreme, number two here is another extreme. When we want to express P of x1, x2, x3, x4 when they are independent from each other. So if they are independent from each other, what we can write here is P of x1 multiplied by P of x2 multiplied by P of x3 multiplied by x4. This is another extreme, that every pixels are independent from each other. Doesn't have any correlation with whatsoever between these pixels. And in this case, if you want to know the probability of this expression, which is now in the red, the expression in the red here, is very simple. Why? Because this one only have well, there is the probability is you find the highest, you know, the probability of this, you find the highest. This only costs you 2. Well, yeah, this is only 2. Wait a minute. Yeah, so basically this one is 2 by 4, right? In this case, it's only 2 multiplied by n. N is the number of your parameters. So this one is only 2 multiplied by 4, which is cost you 8. But this one costs you 2 multiplied by 2 power to 4 is what? 8 to 3, 8, 8 multiplied by 2, 16, right? So that's when if you have a larger numbers, then the difference will be more obvious. Okay, so that's the difference between independent and dependent. So if you make the pixels independent to each other, it's very cheap to compute the probability, but there is no connection between pixels. And if there's no connection between pixels, it's useless because we cannot create a graph on the image. And we can create this graph, this blue graph here, this blue graph here. There's a graph, right? And that graph is actually connecting every pixels. And we can create a graph based on dependent variables. But we cannot create any graph, it's totally dependent. But the first one, the one that is have a graph, is very expensive. It's forbiddenly expensive. And the second one here is very cheap, but doesn't give us anything, doesn't give us any graph. So we have to work in between. So people already thought about this. Markov, which is the name of a person, is a Russian, thought about this, how we can create a system, a graph, connecting all the nodes and still have mathematical property connecting the nodes. And at the same time, it's not expensive to compute. So that's the motivation of Markov random field. So we want to have something in between of these two. So what is something in between? So something in between is called, the techniques itself is called factorization. So factorization means that we have to factorize the dependence of the pixels so that it can be computationally efficient and at the same time still can give you some connection. Okay, so factorization is the basic idea of Markov chain. So Markov chains, again, it is in sequence. So x1, x2, x3. Well, let's forget about sequence. Let's directly talk about field. X4. So we know that if it is blue line, it will be very expensive, especially if you have, imagine that you have x5, x6, x7, x8, x9, right? It's very expensive here because then you have to connect every single here with all the pixels. I cannot write down this because it's very complex now, right? So every pixels you have to connect to each other, in one by one manners. So it will be very, very complex. What people can do if you write this in this way is to have a connector here, and then we have 9, x1, x2, x3, x4, and so on. Right? So you can imagine that, right? So every point have to connect to each other. So that one is not really efficient as we discussed. But Markov, the person called Markov thought about this and give a solution. And the solution is that if you have 9 or whatever the number of nodes that you have, then the connection doesn't need to be one-to-one. The connection can only be considered from the neighbor's point of view. So for example, here, the neighbor of x1 is x2, so then we connect. The neighbor of x1 is also x4, then we connect. And x5 is also the neighbor of x1, but we can ignore that. Because to connect x1 to x5, we can rely on the connection between x2 and x5, or between x4 and x5. So now the connection, according to Markov, is that only based on the neighbor. Okay, so again, this is the illustration of how the construction of Markovian graph. So let's simplify the problem. Consider the 4 nodes. So in this case, now the question is, what will be the x1, x2, x3, x4, right? This is the question that we have in the beginning. How we can express this in Markovian way. In Markovian way, this expression is based on the connection. And this connection here means that we only have P x1 connect with x2, and we have multiply with x2 multiplied by x5, multiplied by x5 multiplied by x4, multiplied by p x1 multiplied by x4. We only have 4 multiplication for 2 variables. 2 variables is much easier to compute than 4 variables or more. It's cheaper. Is it understandable? Right. So this is called factorization. So this one is called factorization. We factorize without sacrificing the connection. We still have a nice connection between x1 and x5 through x2 or x4. Okay. And why this is important, the connection is important, I will give you later on explanation in terms of the graph flow, the flow graph, that you can do the optimization by connecting all the pixels. Okay, but the concept now that is important here is factorization. This one is called factorization that can keep the connection but make the computation more efficient. Any questions so far? Okay, so if there is no questions, in general, the factorization in Markov random field is based on clicks. Okay, so the factorization is based on what is called clique. So what is clique? Clique is a clique is a mutually connected nodes. So in this case, the cliques here is for this the diagram that I show you here. The clique is what? X1, X2, right? Because they are mutually connected. And also X2, X5, X5, X4, and X1, X4. So this connection, mutually connected nodes, are called cliques. So I give you another example. For this one, X1, X2, X3, and X4. If I have this kind of connections of the nodes, what will be the cliques? X1, X2, X3. That's all, and then X2, X4. Yeah, so this is cliques. So in general, the factorization in Markov random field, P of X1 until whatever the number of X that you have, Xn, for example, equals to 1 over Z multiplied by the product of the cliques. Remember, that's this one is the multiplication of the cliques, right? So this is multiplication of a cliques phi C X1 until Xn. That is the definition of this one is actually the definition of undirected graph. And cliques here, depending on how you define the cliques that we want to have, should follow Markovianity. So Markovianity is always depending on the order of Markovianity. So in this case, for example, we have Markovianity order 1 because we just connect the neighbors, one neighbor next to that node. If it is 2 order of Markovianity, means that you have to connect not only the next neighbor, the adjacent neighbor, but also the neighbor of your neighbor. So that's called second order Markovianity. But let's not be confused with this. Let's focus on order 1 Markovianity, means that the connection is only to the adjacent node. Again, the cliques here have to follow Markovianity. Any questions so far? Okay, so if there's no questions, let's look at this example further. So in this case, if you apply this to this graph, to the graph that we have here, so in this case, the definition becomes 1 over Z phi 1 is X1, X2, X3 multiplied by phi 2, which is X2, X4, right? Okay. So now the question is, what is phi, right? What is phi here? Phi is actually the same as probability. So phi of X, for example, X1, X2, X4, for example, is actually the same. You can assume this is the same as probability of X2, X4. You can assume in this way. Now, the question is that if we can use probability, why we have to use phi, right? Why we have in trouble of defining another variable of phi. And this is important for our case. Why? Because probability has certain properties. What is the properties of probability? There are two properties of probability. One is, what is the probability? What is the first property of a probability function? It has to be between 0 and 1. And what is the second property? Yes, the sum or the integral of p of x dx equals to 1. So the first one is okay, although it's a bit difficult to fulfill sometimes, but it's okay. We can normalize. But number 2 is troublesome, because you have to make sure that the sum of this function for all the possible value of x equals to 1. And that's why we don't want to be trapped in this definition of probability. We create another function, phi. Phi is any functions that can make phi proportional to p. So phi of x have to be proportional to p of x. As long as they're proportional, it's okay. Right? And because phi is not a probability function anymore, it's any function, right? But in the end, you want to have probability in the end. In the end, you have to have probability of all x until x1 until xn. Because you want to have a probability in the end, and your function is not a probability function, then you need to have a normalization z. So z is to make sure that your product in the end of the day will give you a probability function, a probability value. So in other words, z here is sum over x1, sum over x2, sum over x3, sum over x4, multiplied by phi x1, x2, x3, multiplied by phi x2, x4. Okay, so z here is a normalization factor. So what do you think about z here? Is it easy to compute or not? Is z easy to compute? No. Why? If you think this sum over sum, if you are a programmer, what does it mean by this? It's nested loop. It's a loop over loop over loop over loop. If you have a 4 variable, there's a 4 in nested loop. If you have 100 variables, then it's 100 loops. Right? And it's very, very expensive. So this one is almost impossible to compute. So z here is prohibitively expensive. Prohibitively expensive. And that's the problem of this definition of z here. As much as possible, later on, we will see, that's why we use MAP. That's why I mentioned about MAP, because MAP can remove z factor here. Okay, all right. Before I get to the real things, right? So all this so far is very abstract mathematical discussion, which is very important because later on we will use this for our discussion. But before I continue, are there any questions here? Okay, so if there is no questions, let's move on to our Markov random field. Markov random field formulation. Okay, so now let's look at the graph. X1, let's put it this way. So X1, X2, X3, X4, and they are connected by graph. So I connect in the Markov-Yanati way. So this is Markov-Yanati connection. And aside from X1, so X1 until X4 are random variables. Anyone have any question on the definition of random variables? Random variables means that we do not know the outcomes. And for example, if you toss a coin, the outcome of this coin is called random variable, because we do not know, and the outcome can change depending on the event, right? So that's called random variable. We do not know, we do not know the values, and the values can change depending on the events. And that's something that we want to know. And aside from this, something that we want to know, yes. Sorry, I cannot hear you. We will talk later on, but assume that it's just total random at the moment. Okay, so we do not know what is the things governing the distribution of the random variables, but we do not have any assumption yet at this point. Assume that we have these random variables, 4 random variables, and we also have observation. So we have T3 here, T4 here. To make it clean, I have this observation. Observation is another thing, right? And the connection is also, because the neighbor of T1 is X1, so I put it in this way, right? What does this graph mean? This graph means that, you know, T1, T2, T3, T4 is called observation. And because it's called observation, it means your pixel value, because pixel value can be observed. So T1, T2, T3, T4 are the observation, the pixel values. And X1, X2, X3, X4, for example, is your depth estimation. So the depth is depending on the observation, of course. Different images will give you different depths. Right? So X1, X2, X3, X4 are the depth values that we want to estimate. But D1, D2, D3, D4 is pixel value. So now you wonder why pixel 2 and pixel 4 doesn't connect. Why they are not connected? Why they are not connected? Anyone can answer this? Why they are not connected? Yes, because they are observation, and why the observation is not connected? Yes, why they are independent? Why the observation are independent? Well, it's very difficult mathematically in terms of explaining this connection, but you can imagine that this D2 and D4 are puppet. A puppet is in the front, but there is a master behind. You know puppet show, right? Puppet show, the puppet doesn't have any connection with the other puppet. They are connected only because of the master. The master are connected, but the puppet themselves, they actually don't really do anything. It depends on the master behind. So that's why D1 and D2 are not connected, because they are just puppets. The real master is actually behind this, and the master here is X2 and X4, because X2, depending on the depth, that will influence the pixel values. If the depth is far away, for example, then the pixel value will be different when this pixel is close by. All right, so that's if you think that the master is the depth, but the master X1, X2, X3, X4 are not just depth. It can be anything. For example, in semantic segmentation or in segmentation. In segmentation, we want to have a foreground and background. For example, this is foreground background segmentation. So I can give you a foreground background segmentation example, like foreground segmentation. Actually, foreground segmentation is one of the not in this way, but it's somehow represented in the assignment. So look at these people walking with the dogs, right? The foreground is the person there, and the rest, the trees, the road, and everything, the house, the buildings are all background. And then we want to know which one is foreground, which one is background. So the random variables here have two choices: random foreground representing foreground and representing background. And this value of D, the pixel value, depending on whether this is foreground or background. All right. So that's the reasons here. Why there is no connection between D2 and D4, because D2 and D4 again are the puppets. They are not the real master behind this formation. Any questions here? And that's why D4 connect to X4, because X4 is the master of D4. Any questions here, anyone? Okay, so if there's no questions, let's move on further. Now, mathematically, how we can describe this, right? Oh, by the way, as I mentioned, it is a graphical model here. This is already a graphical model. And this one is undirected graphical model. Undirected graphical model. Right. So in this case, we want to know what is the probability of x1, x2, x3, x4, and also d1, d2, d3, d4. Oh, because d1, d2, d3, d4. Let me think. Okay, so let's put it in this way first. Yeah. Then, because it's too long, right? It's too long. Then I just want to make it simpler by writing in this way. X and T. But you know the meaning of this, right? This is a joint probability of all X and all D's. And according to the formulation, it's equal to 1 over Z multiplied by what? Anyone? Multiplied by phi. Phi1. Phi1 is what? Or just phi is fine. Phi is x1, x2. And then phi x2, x4. Right. Phi x4, x3. And then phi of x1, x3. And then phi of x1, d1. Phi x2, d2. Phi x3, d3. Phi x4, d4. So this is the probability that we want to compute. Now, because this is too long, again, I can just simplify the writing by using a product and one of a. Okay. Which one is that? This is 100% of it. Yeah. Battery is low. I'm not sure. But anyway, so that seems to be okay. Okay, so anyway, so this one is I equal to 1 until 4 phi xi di multiplied by product of j, j equals to neighboring of I, and this is phi xi xj. Agree with me? Anyone? Well, it's a simplification of the notation, but you know the meaning of that notation, right? So in general, then, if we have P of X and D, then we can write 1 over Z, the product of I equals to 1 until n, phi X I di, sum of j neighbor of I, phi xi it's weird. Here is 100, but here is 10. Yeah, not really sure. But anyway, so this one is xi xj. Right. Now again, the problem that we know before is that z here is very expensive to compute, right? Especially if you have n variables, it's impossible to compute z. So how we can solve this z problem? So to solve this, we use MAP. So we use MAP. In MAP, we try to maximize, we want to find x, obviously here we want to find x, right? The hidden variables, the master behind the observation, behind the patterns. And for this one, we have argument max of all possible of x, p of x and d, then this one is equal to argmax x. We can maximize the x given d. Okay. Anyone have any questions here? Why this is become like that? You know that this product rule, right? X d equals to p of x, sorry, x given d multiplied by p of d. D is a constant, so this one is the probability of the observation is always the same, regardless you change x. D is always constant, so you can forget about this when you're maximizing x, right? So that's why this the expression holds. Right. Okay, so that's the reason why we have this, and then we have argmax over x one over z yeah, 1 over z I equals to 1 until n phi xi di multiplied phi j neighbor of I phi xi xj. Agree, anyone? Agree with this? This one is simply I copy and paste from there. Okay. So now z here, z will be constant. Again, z will be constant regardless whether you change x. So whenever you change x, z will be the same. So you can just remove this out. Max over x sum of I equals to 1 until n phi xi di product j neighbor of I phi xi xj. Okay. So in mathematics, especially in this particular case, we don't like two things. We don't like products. We don't like maximum. Because when we do the maximization, there is no bound, there's no upper bound. Infinity will be the bound. But if you minimize, the bound will be, the lower bound will be 0, right? So minimization is more easy to deal with. So, and to change the product into sum, we have to do what? Logarithmic operation. So we apply logarithmic operation minus logarithmic operation. So if it is minus logarithmic equation, it will be arc mean over x sum of I equal to 1 until n log phi xi di plus sum of j equal to neighbor of I log phi xi xj. Okay, so we are almost there. So the last thing is that arc mean over x log phi is a bit troublesome because you have log, you have phi, and I just put something else. Sum of I equal to 1 until n log phi. I change into f function ft, for example, xi di plus sum of a j neighbor of I log, I don't really like log, so I change that into fp xi xj. So I have a function fd and fp, and by the way, this is the if you put x here that we want to find, and this one is the formulation. This one is the formulation for Markov-Random field. So please keep this in mind. So this one is in the end is Markov-Random field. Oh, by the way, if you don't understand this, you will be forced to understand because this one is your assignment. So this one, the equation here is exactly your assignment. So yeah, you have to understand that one. Even you will understand this one eventually. Okay, so now let's take a look at this equation. Let's copy and paste to make it clean. If you don't understand the derivation, is fine. The derivation is quite long, but you really need to understand the meaning of this. So this is let's put it here. So what is the meaning of this? Okay, so the first one, the first part here, the first part is called data term. The second part is called, anyone knows about this? It's called prior term. So there are two terms in this equation. First is data term, and the second one is a prior term. Data term is specifically called likelihood, and the prior term is prior. So there are some regularization going on here with respect to your likelihood or data term. So how we can use this formulation, for example, in very simple case of denoising. Okay, so let's have an example of image denoising. Image denoising. Oh, by the way, this is the first part of your assignment. Image denoising. So please pay attention on this because this is something that you have to do anyway. So in image denoising, I imagine that you have an image. So this image is your input image. And in your input image, you have a text. So for example, the text is this kind of text, CV, and imagine that this CV is black, for example. Okay, so this is a black pixels. But unfortunately, your input suffer from noise. So a lot of noise here. So a lot of noise. So this is your input. Now, your task is to make them clean. So your task is to make this clean. Something like this. Okay, so you clean up, so then you can have a image that is not suffer from noise. So this is the expected output. So now using this formulation that we have here, how we can deal with this? Right. So in our case here, first of all, when we say about x, right, xi, because there are a lot of x, a lot of pixels, xi is only two things. One is 0 or 1, which also means that this one is foreground or background. Foreground means that this one is CV, the text is foreground. B is the background. Background in this case is the white canvas. Okay, so the background is, in this case, is white, and the foreground is basically black. Well, in the optimization in your computers, you don't have F and B, but you have 0 and 1. 1, 0 or 0, 1 doesn't really matter. Let's see. Right. So any questions so far here? Now that's your X, your random variables. And the random variable is either 0 or 1 or black or white. Okay, so now let's look one by one here. So for the prior term, the definition of the prior term, which is fp, the function of fp, x1 and xj. Now, this is really up to you, but what will be the most common sense way to connect xi and xj? If you have two pixels next to each other, what kind of connection that you expect them to have? Equal, exactly. So equal connection between neighboring pixels is called smoothness constraint. So this one is based on smoothness constraint, means that we encourage them to be equal because we want to minimize. So because you see here, we want to minimize, right? We want to minimize the equation, the objective function. By saying that we want to be equals means that you have to say that xi minus xj equals to 0 because we want to minimize. is that we encourage them to be the same. Right? So again, this is called smoothness constraint. Any question on this? In other words, if you look at the graph, you look at the graph here, x1 and x2 are encouraged to be the same. So this one is basically FP of x1, x2. Okay, so that is FP is there. That's how we create this connection. So by knowing FP, we know this graph here. We know the weights of this edge. The weight of the edges connecting the random variables will be known. You will get some value there. Okay, so we will have all the value for the edges between random variables. We also want to know the value here, the edge between random variables and observation. So we have FD here of x4 and b4 in this case. So we want to also know this one, so then we can have some value there. And if you have the value for all the edges, it is called complete graph. So we want to create a complete graph by having the values for all the edges. Okay, so we have the value for FP. We want to know the value for FD. So the FD is called delta. So by the way, how many possibilities that we will get here? How many possibilities that you will get? How many? How many possible values of FP? 6. Why 6? Someone has mentioned correctly already. It is 4. 4. Why is 4? Because xi has 2 values, right? Possible value of 0 and 1. Xj also has possible value of 0 and 1. So either 0, 0 will give you 0, 0, 1 give you 1, or 1, 0 give you 1, or 1, 1 will give you 0. Well, the possibilities is 2, but the combination is still 4. Yeah. So the combination is 4, the possible value is 2. Okay. That's the possible value of FP here. Okay, so that's FP. Now let's look at FT. So before we get into FT is a bit difficult the most difficult part to model. But the most common sense way, how we can know whether this is foreground and background. FT is actually FT. It involves xi and di, right? You involve the data. The data is there. Di is the data, the RGB value that you have. But the prior doesn't have the data, regardless of the value. It doesn't really matter. That one is not depending on the RGB value. So FP here is independent. The function is independent from RGB value. Nothing to do with your observation. But FT, the data term, have something to do with your data term or data observation. I mean, your observation data. So what is the intuition bit of FD? FD is basically if the pixel is white, it's likely to be background. If the pixel is black, it's likely to be foreground. So that's the easiest intuition of this data term. Data terms is only looking at your pixel value. Oh, this is black, so it's likely to be foreground. Oh, this is white, so it must be background. So that's the idea of this, how we can define this term. So this term is only following the indication from the observation. So basically this one, we want to find a distance function that transforms the pixel of xi to be the same as your RGB value. So what is Txi? Txi is a function when it is if it is xi equals to foreground, for example, or background, and if xi equal to foreground. If this background, then pi is black, and black here the value is 0, 0, 0. So if xi, you assume xi to be black, then t of xi give you the value of 0, 0, 0. And if you assume that xi is the foreground, then it will be white. And the white will give you value of 255, 255, 255. Is it understandable here? So that's the T transformation. In other words, the value of x, so what matters is the value of x here, right? Xi will be encouraged to be the same as indicated by your observation. If your observation of R is black, then xi is likely to equals to background. So background here, for example, what is the background? 1. Foreground is 0. Right. Any questions here, anyone? And that's it, as simple as this one. So we have to, again, here we have to put all the values in the graph. The basic idea is that we want to have a complete graph, right? And in complete graph means that we have to find the value of these edges. And to have the value of these edges of the graph, we have to follow this equation here for FP and FD for this particular example. Again, be careful with the data term. Data term is the most difficult part to do the modeling. Any question here so far? I will explain further on this matter, but I think it's better to have a break first. And yeah, for last call for the questions. If any question before we take a break? Yes. Oh, this one, Max. So I mean, well, what is the answer for this question, everyone? Minus log, yeah. Minus log. If it is minus log, then if it is assume that it is max, right? It is max, then you have minus there for the whole things. For the whole things, you have minus. And max of minus is mean. Max of minus is mean, right? Is that imaginable? Max of minus is mean. So this one is mean. Mean of the positive. So, any questions here? So basically, if you don't understand, you cannot imagine that it's a max here. This is max, right? Then you flip this by multiplying by mean, right? The multiply by mean, then you flip this one, and then it's become mean. Okay. All right. Any other questions? Any other questions, anyone? Okay, if there is no questions, let's have a break and start again at 8:05. We start again at 8:05. Yes.
Wondering in the Simon Day 1 part 4 in image staging. When I use my own home graph matrix to transform the one image to another image, can I use the CV find contours to find the such as the shape of the size of the transformed image. Use the CV dot find the contour function.
Why do you need that function?
I need to compute the size of my transformed image to the image staging, because I need to create a
Canvas.
a canvas, and I need to know my.
I think that should be fine. But email me, CC to the GA, so the GA will be aware that what is the answer for that.
So I can approach to
No, just email me, CC to GA.
CC to GA
Yeah.
about this
question. Yes,
and you will
I will reply.
And the CC to
Yes, GA. So then the GA can be aware that whether I'm allowing this or not.
Okay.
Yes.
Thank you.
Okay, so the last question. Well, better we can show that is used predictive. It's every point in previous country.
Yeah, you can do it. I mean, I have to
Yeah, I understand. Then the consumers must get maybe he and you propose within the same. Then here this is something complex. Size
you can look for one and you have the fact not in one. I don't know if you but that's the answer for your question.
Yeah.
Well, we get your report.
Somehow like interpolation, automatically
It's strange that you mentioned that because it's non-type.
Yeah.
Just a matrix.
That's why non-pi don't do it in a non-pi. You have to put it in the book.
前面我这个来的，
那个这个non-pi，然后我问他这个为什么会必须得到那个，我这个
一个哪来？知道一啊？
就是说这个 f 乘以这个
这个是 I， 是 I， 我说这个是 I， 这个是 I， 不是 D。
Oh, I see, I see. That means you cannot do the play.
Yeah, so nobody wants to see, because see doesn't really matter, we always look at very hard. But I understand the Python is about fancy. So that's why I put in the fraction. That you have to do it for the whole part. But the time, you can just use.
Yes, yes. Thank you.
Because that's the whole point of online part is by using the whole point of this. It's cat.
You know, actually, you also just do the matrix of the
I use the port.
but you actually once use the x prime equals h x, then it's just
The mathematics way, what else I can use? Well, it's not problem, but it's not like I can start. But yeah, there's no, I didn't explain what you get before. But you don't need to worry about before because you can have L. Yeah, so now it goes to X. By the way, it's not X, it's Y. It's only yeah. Yeah, this one is very good. Yeah, so X give you X, give you L. This X multiplied by L give you L. Yeah, but I think sometimes. For example, you can have this it's revolution, right? Some optimal point. So it's likely that this function will be. And we add log. The log is also. The next one is not increasing. If it is increasing this way, you cannot. The next is always in the end here. So the function is not that function. The function is likely to be healthy or some many. Yeah, something like that. You mean that it is like this, and it is maximum, then it will be here. And after you log, it will be here. No, log will not be proportional. Log will be somehow this one, but maybe different. Yes. Yeah. Log is not really important. There's no negative sign, so.
Then because that's where we go from up next to up, then there's
So imagine that the function is something like this. Right? After the log is somehow like this, so it doesn't really matter whether you put log or not. Maximum is means that we want to find this maximum x here, right? X. So when you multiply the whole function, this fx, multiply that with minus 1, what happened then?
the axis.
It's split, right?
Yes.
It's somehow like. So what we want is the same. And then this one is become what? If we consider this function. Yeah, the minimum, right?
Yes.
Yeah, that's the whole point. And we don't like maximum. We only like minimum. Yeah.
Okay. So, so the negative sign comes when we actually have the up mean, right?
Yeah. So max here mean actually you
Here mean here.
max here means here. Then this one is you put minus log, but because it's changed, then the minus is gone.
But why did the minus not go there? Why is there a
So
minus?
max minus is mean
Oh, I think why is there a max minus then? Oh,
because we don't like max. We don't like max, so we deliberately put minus. So then it's become mean. So in order to become mean, we have to put minus log. Is that understandable?
let me think about it.
Hmm.
As well.
Max become mean. Max become mean.
Because
So if you are confused, whatever this one, gx, right? Max, gx, and then max minus gx, right? And then this one, max mean, that is actually a mean. Because this one is something that we want. This one that we want. This one that we want. This one value of x that we want. And we don't really like max. So that's why we apply minimum. We apply minus. And then we can apply minimum, right? In the end of the day, we want to have x. In the end of the day, we want to have x here, right? And it doesn't really matter whether this is up or down, but we like down because that's the bound of 0.
But normally if you introduce minus here, then we want to introduce because minus as well. We can but in this case it doesn't matter.
Yeah, because we just want to have x.
Just one then we just find
Yeah, and then we have to mean without one x. Because in the end of the day, this is something that we want, x is something that we want. Yeah, thanks. Yeah. Can we operate the second side? Okay, so let's start the second session. During the break, there's a few questions on the minimum, maximum, why that's happened in that way. So I want to clarify that one, so then everyone here that have doubt in mind can understand. So imagine that we have, for example, say that your function is a simple function, something like this. After the log, so you have the argument max, let's say gh, right? And we want to have instead of maximum, we want to have minimum. So but the basic intuition is that we want to flip this one in such a way that I'm not really sure how to flip this. Maybe let's oops. Maybe in that way, I'm not sure. Something like this, I think. So that's how we flip this, right? And basically, this is the idea is that we want to find x here. This is g of x, and we want to have this x star, and x star is the maximum. So in the beginning, x star here is the maximum, right? The maximum of function g. And assume that we have another function, and this function is f. Instead of g, it is an f function. And this f function equals to what? Minus g of x, right? Because it's a flip. And in this case, but the x will be the same. And if we want to work on the flip, then we have to make it x star equals to a mean of f of x. That's the idea, right? Because they are gx or fx are the same actually. Well, they are not really the same, but they are the opposite of each other. But x star will be the same, exactly the same. Doesn't really matter whether it's maximum or minimum. And this x is something that we want to find, right? Any questions on this? So that's actually the answer for your questions on this. In other words, here fd of xi di equals to minus log phi xi di. That's how you flip. Any questions here? The same apply for FP. Okay, so if there's no question, let's continue with this one. There are many things happening here. Let's look at the, as I mentioned again, FP, right, have two possible values, 0 and 1. 0 is the same if xi equal to xi equal to xj, and 1 if xi is different from xj. There are two possible values of fp. So to be complete, I can write fp of xi xj in that way. Now, the question is, how about fd, right? What will be the possible value of d? Well, the possible value of d here is a lot, because we are talking about the distance between RGB values, right? So let me think. So here again, but fd and xi here have two possibilities as well. Depending on di, of course, fd for let me think here. For fd, if txi equals to 0, 0, 0, 0, 0, 0, if again if xi equals to background and t of xi equals to 255, 255, 255, 255, if xi equal to foreground. Okay, so in other words, basically fd will give you some value. Well, this is fd, but this one is t. But you know, I mean here that fd depending on the value of tx and ty, and tx when x equal to b or x equal to f. Okay, so anyway, so this is not concrete yet. So I will show you soon how we can optimize this. Let me think how work it best. Okay, so maybe I will explain it this way. So after we have fd and fp, right? So we have x1, x2, x3, x4, and then we have t1, t2, t4, and t3. Then we have connection here for the prior. It means that we will have a value of fp of x1, x2, and we also have fd here of x2 and t2, and of course we have all the d here, fd of x4, t4, and so on and so forth, right? So you can imagine that all these have some value. All these have some value. It means that our graph is now complete. We have a complete graph. Now, if you have a complete graph, the question is how we can optimize this. How we can optimize this equation. We now have all the value, but the question is how we can optimize it. So what does it mean by optimizing it? Optimizing it means that, as I mentioned again in the illustration that I just gave to you, is that we want to find a function when it is minimum now. If your total function is something like that, we want to have some value here that indicate your x star. Well, the problem is that your x star is in a high dimensionality. It's not just one axis, but in many different axes. If you have 4 pixels, it will be 4 dimensionality. If you have 10,000 pixels, then it will be 10,000 dimensionality. So you can see here the optimization become a problem. How we can optimize it and how we can find that particular point that can minimize the error function. Or in other words, we want to optimize the probability here. So how we can optimize the probability of this Markov chain, Markov field. Okay, so anyway, so that's the whole point. To make it clean first. Right, so there are a few different ways to optimizing graph. So this is a problem of which is called graph optimization. Graph optimization. So in graph optimization, one of the possibility is using graph cards. This is one of the techniques of graph cards. The second technique is called belief propagation. The third one is called convex optimization. So there's a lot of different techniques to optimize this graph. And in this course, we will focus on graph card and touch a bit on belief propagation. Okay. So now let's talk about graph cards. So when we say that we want to optimize this, you know the meaning of this, right? The meaning is that choose x, the value of x for all x's, x1, x2, x3, x4, and so on. Choose the value of x in such a way that this error function become low as possible. So that's the idea of this optimization. And this is a possible, this is a combinatoric problem, because x1 can be 0 or 1, x2 can be 1 or 0, x3 can be 1 or 0, and so on and so forth. So, and they are connected. x1 and x2 are connected to each other, and so on and so forth. So this is a typical problem. But the idea of graph cards, can be illustrated in this lecture note here. Let's see which one is that. Okay, so you can imagine in this way. So this is something to do with our background foreground segmentation or denoising. So imagine that you have this input image here. This is your input image. And then we transform this input image into graph. So this is the graph that you will have after you use the formula that we have, FT and FP, the likelihood and the prior. And when we have this graph, the idea of graph cuts is to cut this one. So to find the path here, the path in this case, that path, and then you cut. The left one becomes red, the right one becomes blue. And based on that, then you can have a proper segmentation. So this is the output of your segmentation. So that's really the basic idea of graph cuts. In other words, we have to find first the graph, we have to define the graph, a full graph, complete graph. And after we have a complete graph, then we do the cutting to have the optimization. Now, the problem is that how we can cut this optimally. Okay, so that comes to the theory of graph cuts. Okay, so in graph cut, let's have the simple example first. So imagine that you only have x1 and x2 to simplify the problem. And we connect these two because x1 and x2 are adjacent nodes, adjacent pixels next to each other. And in this case, we will have, we also have D1 and D2, right? And after we compute FD and FP, we will have FP x1, x2. We will have FD x1, d1. We will have FD x2, d2. Okay. But again, we do not know x1 and x2. The problem is that we do not know x1 and x2. So in this case, we have to assume x1 equals to background, for example. Or maybe you can put it foreground, it's also fine, foreground. If we assume x1 is foreground, then FD x1 equals to foreground given di. You assume that x1 to be foreground. And what will be the distance between x1, which is assumed to be foreground, from your di? Is it understandable? So for example, if your di is happen to be white. So if your di equals to white, which is 255, 255, 255, then this one equals to what? What is the distance here now? What is F? F is foreground. Foreground means what? Foreground means P of xi equal to F equals to black, right? Foreground is black. So this will be equal to 0, 0, 0. So what is the distance between 255, 255, 255 minus 0, 0, 0, 0, right? Well, in this case, of course, you cannot have this, you can convert this into scalar because this one is RGB. But you can simplify the problem like 255 plus 255 plus 255 in this case, which is a big number, 255 multiplied by 3 basically. But this one is a number here. There's a number here. Okay, that's how you can get FD. You have to assume that FD equal to F in this case. Now you also have to assume that XI equals to P, background. If you assume that XI equal to background, then P of XI equal to background equals to what? Equals to white pixels. And white pixel is 255, 255, 255. Correct? So then what would be FD if you assume x1 equals to background and you are given di, and again your di, remember your di is what? Your di is this one, right? That's your di. Di doesn't change because di is the observed pixels, doesn't change depending on your image. So in this case, FD equals to what? 255 minus 255 all along the way equals to 0. So there is a two possible values for this FD. So this FD here in this graph here, FD, there are two possible values. When you assume xi equal to foreground or xi equals to background. Any questions here? And this is the same as FD here as well. The FD x2 d2 also have two possible values. Okay, so although this one, the edge here are just one edge, but actually each of these edges have two values, two different values. So I hope you can understand that. So now, in graph cards, we actually don't really work on this graph. in graph cards, we work on what is called source and sink graph or SP graph. So we have source and T. You can assume S or source as foreground. You can assume this in this way, so it doesn't really matter what you assume. It can be background or foreground, but let's stick with this foreground and background to make it easy. And you have two nodes, which is X1. You have to transform this into this kind of graph, SP graph or source sink graph. And in this case, you also have a connection between all these. So this connection here, let's have this connection first. X1 connect to S. X1 connect to B. When X1 connect to connect to S, I mean, that's when we apply this one, when we apply this assumption, when we assume Xi equals to F. That's the connection when Xi and S. So what value that you will have here for our example? What will be the value there? According to the example that we have, what will be the value? Anyone? When X1 equals to F, then FD equals to 255 multiplied by 3, which is this one. That's when we assume that X1 equals to F. When we assume that X1 equals to background, which is X1 equal to T, it is equal to 0. This one is referring to this one. Is it understandable? Anyone? Oh, by the way, this is your assignment. So you have to be able to define this graph, because otherwise you will not be able to do the optimization. If you have any question, please ask. Again, this is part of your assignment. You have to be able to define the graph. Okay, so anyway, as you can see, there are two possible values for this binary classification, right? So we have this one and that one. It means that in the end of the day, we also do the same for this side here. X2 assumed to be foreground, X2 assumed to be background. So you have that one. So to make it clear, so we have S. We have S here, we have T, we have X1, we have X2, and then we have graph here in this, the likelihood graph, the data term graph. So you have F, D, we have F, D, X1 equals to what? X1 equals to foreground or S in this case, D1, and in this bottom here, XFD, X1 equals to T given D1, right? So the same here, FD, X2 equals to S given D2, FD, X2 equals to T, D2. All right, so we have all the values now in this graph, except the middle here. The middle here, they actually have two connections. This one called FP. So again, FP have 4 possible values actually, for combination. But we can assume that when for FP, we can assume there are only 2, 0 and 1. 0 if they are the same, if Xi equals to Xj, and if Xi different from Xj. Now, in the package that you will be using, so in the package that you will use called graph cuts, we don't define when fp equal to 0, because fp equal to 0 is obviously 0, right? When they're the same, the label are the same, is 0 anyway, so we don't define 0. So in other words, in the package that you are using, we only have one possible connection. Actually 2, but we remove 1 because 1 is quite obvious equal to 0. But 1 here is not necessary to be 1 all the time, depending on the number of your labels. In this case, we only have 2 labels, foreground and background. But if you have 3 labels or 4 labels, it's not necessary to be 1. So that's why 1 is still kept there. So this one is for the prior. So this one is for fp xi xj. For the binary, in our case, it can, it's just 1 or certain number. Okay, anyway, so this is the graph that we have. This is called ST graph. So this graph here called ST graph. And this is the graph that's important for optimization. We will optimize the graph based on this graph to get the cut. So we have to cut so the idea is that we want to cut this. For example, if the cut is this way and that way, if I cut in that way, means that x1 is decided to be foreground and background. It is actually background. So when you cut, it belongs to that one. Because we minimize, we're not optimizing, we're not maximizing, but we are minimizing. Because we're minimizing, and the cut is actually when it is minimum. But I will explain that later on, don't worry about that. But the idea is that once you can cut the graph, you know the label of the pixels, of the nodes. Okay, so that's cutting is very important. Any questions here for the intuition behind the graph cuts? Okay, so now let's take a look at the very real example how it works. Okay. Right. So let's have 2 nodes. Example here. Let's have x1 and you have x2, and you have d1, and then you have d2, and this is connected in this way. And assume that the value that you have is here is 1, right? And that because there are 2 possible in binary classification or binary labels, there are 2 possible values. So I will give you 2 or 5, for example, and 9 or 4. What does it mean by that? It will be more obvious if you look at the ST graph. In ST graph, as t x1 x2, so in this case this one is obviously 1, right? But this one actually have two connection. Let's put it 1 and 1, and 2 is when we assume x1 equal to s, and 5 when we assume x1 equal to t, 9 when we assume x2 equal to s, and 4 when we assume x2 equals to t. Okay, so this is the graph, ST graph that we want to optimize. So what does it mean to optimize? Let's assume the simplest naive cut, right? The naive cut will be, for example, in this green line. Green line is the naive cut. So if I cut in this way, I cut in that way. So if I cut in that way, x1 equals to what? What is the label of x1? Is the label of x1 will be s. The label of x2 will be s as well. Okay, so if I cut in this way, that's the label that you will get. But then, what will be the cost of cutting this cut? It is 9 plus 2, which is 11. That's the cost of cutting these two edges. So now the question is here, how we can cut the graph in such a way that the cost must be minimum. What will be the cost of with the cut that the cost will be minimum? So let's look at this possible cut, the red one. The red one there. So what is the cost here? Anyone? Well, it seems like 8, but it's not 8 because later on you will see after optimization, you will see later on, but it cannot be seen now. But you can trust me first that this one is 2 by plus 1 plus 4, which is 7. Okay, so the basic idea of graph cuts is to find the cut that is minimum. And in this case, the minimum is x1 equal to s, x2 equals to t. So how we can get into these techniques to find the minimum cut, right? So the techniques that is to find the minimum cut, it's called Fulkerson method. How many of you know about Fulkerson method? How many of you from CS, from computer science? Oh, okay, so none of you. Okay. In CS, actually, you learn about this. This is part of algorithms and data structure. But anyway, so if you don't learn this before, the Fulkerson algorithm, there are 3 basic components. So there are 3 basic components. One is called capacity graph. The second is called flow graph. And the third is called residual graph or residual graph. So what is the capacity graph? Capacity graph is exactly what you have here. So S and T, and x1, x2. So in this case, we have 2, 9, 1, 1, 5, 4. That is the capacity graph. Flow graph, I will tell you later on. Flow graph, x1, x2, t, something like this. So the basic idea of flow graph is to think the graph as a pipe. You know, pipe. If you have a pipe, then you can flow water inside the pipe. Okay, so we have water, so that's why S is called source, because we imagine water's source of water. So S is the water, and 2 and 9 are the pipes. And 2 here is the capacity of your pipe. Your pipe can only take 2 liters of water. And the other side it can have a capacity of 9 liters of water. So it's the bigger pipe. Now, flow graph basically try to make the flow for the whole pipes to be maximum. We want to maximizing the flow. We want to maximize the infrastructure that we have, the pipes that we have. We want to maximize the flow of the water in the pipe. So if you want to maximize the flow, well, obviously, you can put 2 here, right? 2 is the flow of the water. Because we have 2 capacity of water, we put 2 liters inside, and then the water will flow. Because the next one is 5, have the capacity of 5, the pipe is big enough to handle 2, so you will have 2 there. Sorry, is that true? Yeah, you have 2 there. That's right. You have 2 in the beginning and then flow down 2 liters. So 2 liters is flowing now. But you still have the capacity because the other side, you have 9. What do you do at 9? How many liters of water that you want to put on the 9? 4 exactly. Why 4? Why not 9? Because if you put 9, the downstream of the pipe cannot handle it. The downstream only have 4. Even you put 9 is useless because the downstream pipes cannot handle it. So you put 4 here. 9 obviously can handle 4, and this one can handle 4. It's good, right? Is it maximum already? No. Why is not maximum? Yes, the middle have 1. So you plus 1 here, then it's flow there, and plus here, flowing in the other side. Now the question is it optimum now? The flow is optimum or not? I think it's optimum, right? Because there's no other way to flow the additional water. So in this case, what will be the max flow? What will be the max flow of this? The maximum flow, the maximum water flowing, which is called max flow. What will be the max flow value? 7. The 7 liters is the capacity of your whole system. Why you get 7? When you can look at this, you can look at the sum of this, the sum of the source, or the sum of the sink. They are the same thing. There are 7, both of them. Okay, so this is called flow graph. And once you have the flow graph, you can minus the capacity graph with the flow graph, and then you will get residual graph. Okay, so in this case, because 2 minus 2 will give you 0, 9 minus 5 give you 4, 5 minus 3 is 2, 4 minus 4, 0, this one is 0, this one is 1, right? So when we call mean cut, we refer to this cut here. Which one is the mean cut? The mean cut is this one, right? 1, 2, 3. And if you look at the capacity graph, the cost of this mean cut is 4 plus 1 plus 2, which equals to 7. So this is the optimum condition of cut when the max flow here the same as mean cut. This is the condition when they are optimum. The optimum condition of the cuts is reached when the max flow equals to mean cut. And that's why the test 1, 0, 0, 0 are the optimum cut, which is 7. So 7 is the minimum cost of your cut. For this particular example, it means that x1 belongs to S, because that's the minimum, right? Let's give you 0. And x2 belongs to T, which is 0. And remember that we want to minimize the graph, not to maximize the graph. That's why that belongs to 0 cut. Any questions here? Oh, by the way, the other name of this algorithm is max flow mean cut algorithm. Max flow mean cut algorithm. So you can look at Wikipedia on this algorithm, max flow mean cut algorithm. Any question, anyone? Any questions? Okay, so if there's no questions, let's look at the other example. How to make it computationally easier, right? To have this mean cut max flow. So we have previously 2, 9, 5, 4, 1, 1. So how we can efficiently compute the max flow mean cut is that you flow water too, right? Because we are two, it is optimum. You cannot flow more water. You flow the water there. If you flow the water there, it's not optimum yet. They still have some capacity. So 9 here, you put 5. 1 will flow down here, and the other 4 is here. So this is saturated already. Saturated means that you cannot flow any water. So this is saturated, and plus 1 here, this has some capacity. So what will be the mean cut? The mean cut will be equal to 7, right? 4 by plus 1 plus 2. And max flow, obviously, 2 plus 5, which is 7. So how that you calculate this one by hand? Of course, you don't do it by hand because there's 10,000 of nodes. But if you have to do it by hand, this is the way to do it. Okay, so let's have another example. Something more interesting. S, T, x1, x2. Let's put 5, 3, 1, 1, and 4 and 4. So where do you want to start? Anyone? Start from 5, for example, right? 5, 4 will go in here, 1 will be going there, so this is saturated, 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 and then plus 1. Yes. And then 3, you can put 3 here, and then, oh, sorry, this is not plus 150, plus 1, plus 3. This is saturated, this is saturated. Okay, right? So now the question is, which one that you have, what kind of label that you have to create for this? Because every one is 0, right? Everyone is, the mid cut is 0. So, well, there are freedom here. You can, let me think. Okay, so if we cut in this way, what will be the mean cut? Mean cut equals to 8. Max flow here is also, max flow is equal to 8. So this is actually optimum. If we cut in that way, it's okay. It's a good cut. So let's cut in the different way. So let's cut in this way. So in this way, mean cut equals to what? Is also 8. Max flow is also 8. So this is also optimum. So you can have x1 equals to x2 equals to s. There's nothing wrong with this. This is an ambiguity basically, right? So let's have another one. Another one. Let's cut the red one here. So the red one is this one, and then I cut this one, and I cut that one. So the mean cut equals to what? Equals to 10. And actually max flow equals to 8. Max flow doesn't change when you change the cut. All right. So in this case, this is not optimum. It's not optimum. Because it's not optimum, you don't choose this one. The other choices are good. The blue one and the green one are good, but not this choice for the red one. Okay, so that's how you assess optimality here. Any questions, anyone? Okay, so if there's no questions, let's have another final example. Let's make it more complicated. X1, X2, X3. So we have 5, 8, 2, 4, 1, 1, 3, 3, 2, 4. Okay, so in this case, let's start with, for example, 5. 5, 5, this one is 3, so you still have 2, right? 2 going to this way, and then make it this 2, right? So this one is saturated, saturated, and saturated. Okay, so now what do you want to do next? Which one? Let's say that this is 2 here, right? 2 here is easy, saturated, that one, and that's it. And 8, what would be the best way to put 8? Anyone? What is the flow that you want to put for 8? Anyone? 2. Are you sure? 2 going to where? It's only 1, right? Only 1 because it's going this way. The only plus 1 here. That's the only choice. Okay, so that's the situation that we have. And in this case, if we have to cut, then we have to cut this one because that one is saturated. We have to cut that one because this is also saturated. This one also saturated. 1 is saturated there. And that's right. So there's a 3 here. There's 3 cut here. Well, there are 5. So now there are 2 choices here. Number 1 and number 2. And we have to choose which one is more optimum than the other. So if you choose number 3, if you choose number 2, what will be the cost? 2 plus 1 plus 2 plus 3 equals to 8. Right? Is that true? This is mean cut. I mean, this is mean cut. And what is max flow, by the way? Max flow is 8. So this one is actually optimum already. This cut is actually optimum. But if you choose number 1, what will be the cost? 2 plus 1 plus 2 plus 5. Correct? And this one equals to 10. Doesn't match. So in that case, choice number 1 is a bad choice because that is not optimum. But choice 2 is better because that one gives you the optimum value. And that's how you choose the label. So the label here, in the end of the day, the label for x1 equals to t, x2 equals to t, x3 equals to s. That's how you do the labeling, the classification of the pixels. So as you can see here, the flow of the graph, the mean cut, max flow algorithms, flowing the water means that it's connecting all the edges, connecting all the nodes. Remember in the beginning of this course today, we tried to connect pixels, right? And if it's connecting all of them connecting to each other, x1, x2 connect, x3, x1 connect, and all connect to one each other, it will be very expensive. But as you can see here, even though we just use Markov connection, with the flow of water, they are somehow connected. In other words, the optimization that we do here is called global optimization. It's not local optimization, but it's global because it's connecting all the nodes. So even though your node is on the left and on the top left, on the bottom right, they are connected by this flow of water. So that's why it is called global optimization. And this global optimization is computationally feasible, means that it's not prohibitively expensive and can still optimum. Right? So that's why this is quite important, and to some extent it's a breakthrough at that time in computer science. Actually, in computer vision, in 1990 to early 2000, before deep learning, this one is one of the most popular approach in computer vision, right? Because this is kind of optimization that can be efficient because it's global optimization. Okay, Any questions, anyone? Any questions? As I mentioned, this one is your assignment, second assignment, part 1. So you have to define a graph. Oh, by the way, all this definition of the graph will be all parts, part 1, part 2, part 3, and part 4, all using graphs. So you have to be able to define graph and do the optimization for your graphs. Right. Final call for the questions. Okay, so if there are no questions, that's all today. And thank you, everyone. I will see you next week again. Thank you.
Yeah, we need to cut the
One minute.